Okay, so it's a pleasure to introduce Manos Zafeiropoulos from the Technion, talk about Poissonian correlations, higher orders and weaker variance.
Thank you very much. And something easier after the nice of prior. And I will start by something very easy, which is the concept of uniform distribution. We all know what uniform distribution is. If you take a sequence xn in the unit interval, we're always going to focus, everything is going to be inside the unit interval. Okay? This sequence is called uniformly distributed modulo 1. If for any subinterval, so for any alpha less than beta between 0 and 1, we have that the limit as n tends to infinity of the number of points that lie within the subinterval, the number of terms such that alpha is less than xn, less than beta, and is divided by n normalized. If this limit is equal to beta minus alpha, the collective interval. So then we say that the sequence xn is uniformly distributed modulo 1. And what is like from a probabilistic point of view? What is a property of uniform distribution modulo 1? The thing is that uniform distribution modulo 1. This can be viewed as a pseudo randomness criteria. And what does that mean? What do I mean by this? This means that if you take a sequence of random variables, which I denote by capital Xn, and these are random variables which are independent and identically distributed, and they all follow the uniform distribution in the unit interval. Now these are not numbers; these are random variables. Then the probability 1, or otherwise almost surely, the realization of random variables like xn of omega, which is now a sequence in the unit interval. Just a historical system. Then the probability 1, almost surely, this sequence of real numbers is going to be QD mod 1. Now, this is a property of sequence that we all know. This is very fundamental. What is the property now of Poissonian correlations? What are these pair correlations? Now, if you take any initial segment of the sequence, like the first capital N terms of the sequence, then we define the pair correlation constant function. We note it by R2 of S and N. And this is defined as the number of distinct terms, distinct points. So I take indices n and n that are distinct, and I count how many of them correspond to points xm and xn, such that their distance modulo 1 is less than s over n. Here I have to normalize again by 1 over n. And this is a function of any scale s greater than 0.
It's you have a sequence, use xn, and then you form this.
Right. Here, this is the distance modulo 1. So it's the distance of the torus. And why did I divide by n here? If you see it as like something random, if you suspect that these are random variables here, following again the uniform distribution, then you have a test interval of length 2s over n. You have n to the square roughly many points. So you need to normalize again by n. And this is the reason why we normalize by n. So we do not divide by the number of points here. This is the pair correlation common function. And finally, we say about the sequence, we consider that it has Poissonian pair correlations. Henceforth abbreviated by PPC. If this pair correlation constant function, if it converges to the expected value 2s for all choices of the scale s greater than 0. And how does this notion come into mind? Basically, just like I should mention, just like uniform distribution, this is another pseudo-randomness property of sequences.
Just to reality check, if I take s equals 1,
Mhm.
No. Okay.
So it is another pseudo-randomness property in the sense that if you take xm to be independent, uniformly distributed random variables, then again, almost surely, this sequence here, xn of omega, this will have Poissonian pair correlations.
So where does the word Poisson comes from? What is Poissonian?
It comes because of this pseudo-randomness property. We call this behavior the Poissonian behavior, because if you take this sequence, random variables, then with probability 1, all the gaps are going to be exponential. Then the second neighbors are going to be I'm going to follow the gamma distribution with parameter 2 and so on. Generally, this is referred to in the literature as Poissonian, because it comes also from the Poisson process. Because if you take the Poisson process on the line, then it will satisfy a property like this. But really, it was also another question I had, but I couldn't understand whether Poisson distribution comes into play. And this is what it's called.
And this statement that you just mentioned, is this an exercise or
This here.
Yeah.
No, it's an exercise with just needed variance. So you consider this of the random variable. You take the expectation, which is 2s plus error. Then the variance can be bounded off. And almost surely this will converge to the mean. So at this point, in order to understand the Poissonian pair correlation property a little better, I shouldn't give an example of a sequence which has Poissonian pair correlations, but a sequence that does not have Poissonian pair correlations. So take, for example, Kronecker sequence. The fractional parts of n times alpha, where alpha is an irrational number. And now we know very well that when we see this sequence mode 1, here it looks like this. Here is alpha, 2 alpha, 3 alpha, 4 alpha, 5 alpha, and so on. And it has a very good structure here. We know the 3 gaps theory, that at any stage here, the possible lengths of consecutive intervals that we see in this picture, they can take at most 3 values. Sometimes they take 2 values, some stages they take 3 values. So we will show that this sequence here does not have Poissonian pair correlations because of this phenomenon. And indeed, by continuity fraction theory, we can write alpha as the nth convergent Pn over Qn plus some error term, which is theta n over 2 Qn to the square. Here the theta can be negative or positive, but for infinitely many values of n, let's assume without loss of generality it's a positive number. And then we look at the points I times alpha modulo 1. Then these points are equal to IPN over Qn plus I theta n over 2 Qn to the square. Now, because these are co-prime, Pn over Qn, this is going to be an integer ji over Qn plus an error term, plus a small error here, which is going to be between 0 and 1 over 2 Qn. So the thing is that if I try to see where these points are located in the unit interval, I can split the interval into smaller intervals of length 1 over Qn. And all of these points, I times alpha, or I plus 1, 2 up to Qn, they're going to be in the first half of these smaller intervals. So here is the first half, some point will be here, another point will be here, another point will be here, another one will be there. And this means that for S less than half, the number of distinct indices such that I alpha minus J alpha. I just want to count how many points from all these here have distance less than S over Qn modulo 1. Now, if we choose S to be less than half, if we choose S to be sufficiently small, there are not going to be such points, right? So this means that the limit of the Poissonian pair correlation of the function is going to be 0 on these small scales. And therefore, such a sequence does not have Poissonian pair correlations. And the reason, the heuristic reason why this sequence does not have Poissonian pair correlations is this very good gap structure. The sequence is too structured to have Poissonian pair correlations.
You're not using this stuff. In the proof, you didn't use this stuff.
Yeah, not precisely the three gaps here.
But let's use this good approximation.
Yeah. Now we have seen a sequence which does not have PPC, but it is uniformly distributed modulo 1. And until recently, until 2018, 17, I think, I'm not sure, it was open what is the true relation, what is the true implication between uniform distribution and PPC. So it was proven very recently. This was shown by Eisleitner and Lachman and Lefkut, if I'm not mistaken. No, Bosinger.
I think, by the way, the ice light now will be here.
I know. And this was also shown independently by Grepstadt. There were two different groups. They basically showed that if a sequence has Poissonian pair correlations, then it is uniformly distributed. And actually, Christoph told me that they set up to show that they set up to prove a counterexample of a sequence with Poissonian pair correlations, which is not uniformly distributed. And then they realized the reason why it has to be uniformly distributed. So Poissonian pair correlations are stronger than uniform distribution. And
How did it prove?
say it again?
How did it prove?
Not very hard.
Damping.
Yeah. Roughly there.
Variable is damping.
And it's like elementary.
Yeah, I would say so. It has to do with distributional properties. If we have time at the end, I can reproduce it very within one. Like a brief outline, or whatever. So there were some different proofs following this one. Another proof by Steineberger, which used harmonic analysis. Another proof by Markov, more general setup. But what is interesting here in the first proof, in the 10 pages paper, was something stronger that we proved here. So Eisleitner, Bosinger, they showed something stronger. And this stronger result says the following. Suppose you take a sequence xn, and this sequence has a unique distribution function. What do I mean by this? Distribution function is like some g of x, which is defined to be the limit of 1 over n times the number of terms up to capital N. So this is what we call a distribution function for some sequence. If this distribution function is also absolutely continuous, and its corresponding density function.
So by the way, we call it equidistributed. That's the standard terminology.
It's not equidistributed. It's like
No, I know that you are using different set of terminology, but in the language of people in here, not, I'm aware that it's kind of a conflicting terminology. But we say equidistributed, we mean that the averaging, that the counting measures along x1 up to xn
right.
are converging with star to some limit measure.
Right.
And this is what you mean. So we call it equidistributing towards
Okay, with respect to,
But,
to the corresponding
I know
measure.
that
Yeah, yeah,
you're
yeah.
referring to equidistribution towards the uniform.
Yeah, this one is not necessary. So in the arbitrary case, so in other words, if this sequence is equidistributed with respect to this, yeah, to the corresponding measure here, which is absolutely continuous with density function G. Then under this assumption, we have some, we can deduce something for the pair correlation counting function. And the lim sup as n goes to infinity of this, for which values of s, here you have to take another lim sup. So you need to consider the large enough scales s. This is greater than 2s. Times the second moment of this, of the density function. And also, if in case this does not have, this is not absolutely continuous, this lim sup there is infinite. So it holds even in the absolutely continuous case. And from this statement, one can deduce the thing that the statement that PDC imply uniform distribution, because if the sequence is not uniformly distributed, then this density is going to have a second moment which is strictly greater than 1. And therefore, this limit here will have to be strictly greater than 2s. So this is minimized when the sequence is uniformly distributed. Now these are the pair correlations.
What does S goes to infinity?
Say again?
S goes to infinity or to 0?
Infinity. It's the lim sup here.
It's like shrinking targets of a bigger and bigger.
That's not the right.
Right. So here first you let this statement, first you let n go to infinity and then s go to infinity. But in this definition, you fix the s and you let the n go to. Now these are the pair correlations, which are also called correlations of order 2. And what happens if you consider the high order correlations? Similarly to these definitions, one can define a counting function of correlations of order k. Here you need k minus 1 scales. And this is defined to be 1 over n times the number of indices I1, I2, is equal to up to ik. These are indices between 1 and n, and these are distinct And this means that the pairwise is distinct. And I count how many points xi1 minus xi2 are less than s1 over n, xi1 minus xi3 and less than s2 over n, xi1 minus xik are less than sk minus 1 over n. And as you can also expect, we say that the sequence xn has Poissonian correlations of kth order. If this counting function converges to the expected value 2s1 times 2s2 times 2sk minus 1 for any chosen states.
I'm confused regarding the geometrically. What are you counting? So, how should I think of this? Of this ratio, 1 over n times the number of.
One way, this is one way to think about this. You can also think with
You're
test.
counting some phenomena. Can you explain what are you counting?
Right. You count how many distinct indices you can take. If you look. Zero to 1. How many configurations of J tuples inside the first elements can be extracted, such that here is xi1, xi2, xi3, and so on, such that xi1 minus xi2.
And I understand
Yeah.
what you wrote, but there is a strong intuition that there is some k-dimensional box.
Right.
S1 over n, S2 over n, etc. And
Right.
the product of the two SIs is the big measure of that box.
Mhm.
But I find it hard to complete this picture. So I have this box and I'm counting points in that box. What's
No, you have to count maybe these
different
I'm looking at the point x1 up to x capital N, which is like a point in a huge Euclidean space. And I'm considering all projections to k-dimensional axis. Like choosing a tuple I1 up to ik is just like projecting this n-dimensional point to a k-dimensional space. And you are asking when is it super clustered?
I think the key is that you don't look when point when the differences are
Yeah, so the differences mean that your point was projected to very close to the diagonal. Like
yeah, somehow.
xi1 is very close to xi3 and xi.
Yes, are you confused because we have the xi1 appearing in all of the differences here?
No, I'm just trying to understand what is this. I mean, someone came up with this
Right.
definition, right?
Right.
What was behind what did he think? It applies also to the first definition. What is R2 as an count?
This definition, to the best of my knowledge, this came from something in physics, in mathematical physics. Or I've read that there is also like background in statistical mechanics in these areas, but I'm not aware of all of this. There is some conjecture in mathematical physics that has to do with the eigenvalues of some. Some energy. Right. It's called the very double conjecture. I don't remember the assumptions of this.
I know that I'm kind of cutting the flow of the, but it's just I'm allowing myself. So if you look at x1 up to x capital N, and so this is one point in a huge dimensional space, 0, 1 to the capital N. You can project it to be a finite set in 0, 1 times 0, 1. Namely, you take all pairs xn, xn, like your xm and n.
Right.
So you get capital N squared points in the unit square.
Right.
And your requirement xm minus xn is less than s over n is saying that you're counting how many points are as closely to the diagonal. Now the area of the diagonal is exactly 1 over n, roughly up to a constant. It's 1 over n, right? It's two-dimensional square, and you are taking the diagonal. So someone produced to you a random point x1 up to x capital N in huge dimensional space, and you cooked up a random set in the plane, and an R2SN asks, what's the weight of the diagonal? Of the S neighborhood of the diagonal.
Right.
So it's very, I don't know, now it kind of makes sense to the concentration. It makes sense that the equidistribution of it's a higher dimensional equidistribution statement, saying that the limit as n goes to infinity, R to Sn goes to 2s. It tells you something about what's the asymptotic weight of the diagonal, neighborhoods of the diagonal for this induced process on the plane.
Right.
On this, I don't know, just.
Basically, I imagine it as every isolated point xm needs to have its own correct share of the distribution around it. Where were we? Okay, and these are the correlations of order 2. These are the correlations of order 5. Orders k greater than 2. And one thing we were able to show with Manuel Hauke is basically that this phenomenon there can be repeated for correlations of higher orders, precisely as it is. So, how much time do you have left? An hour?
Yeah.
Oh, okay. So,
slightly more.
In the sequence as Poissonian correlations order k. Then it is uniformly distributed modulo 1. And in addition, this quantitative result of Leitner and Lachman and Poissonian holds. So if g of x is the distribution function of the sequence, then you have the same statement. Here I write all scales equal. From s greater than 0, I send this to infinity. And this limit is going to be greater than 2s to the k minus 1 multiplied by the k minus 1 moment of the density function g.
Again, what is the lim sup over S? Not really. I mean, on the right side, you have something with S. On the left side,
Right. I wrote it here. Here. Sorry. And I was wondering, why didn't we make it one line? Yeah. I was copying it yesterday, and I was wondering, why didn't we make it one line? It looks better than one line. So I made that for infinite remaining, but I would like to this is it. Yeah. This is the density. Of G. Now I will mention an open question. But I want
students.
yeah, nice. So maybe you can do it. Okay, we show that Poissonian correlations of order 2 imply uniform distribution.
Give them something hard.
Yeah, Poissonian correlations of order 3, they imply correlations of order 4, blah, blah, blah. If you have a sequence with Poissonian correlations of order k plus 1, is it going to have Poissonian correlations of order k or not? So I assume we believe that this is not true. No, because these are like this property of Poissonian correlations of some order k is like some moment, the kth moment of something, some function which I can write later in the end if we have time. But there is no reason why the behavior of one moment should determine the behavior of the other. They're like, they can be different. Even though if you have Poissonian correlations of order k plus 1, then this tells you simply by Poissonian that the kth order correlation, they cannot explode too much. They will be restricted, they will be close to the Poissonian limit, but maybe they will do a little oscillate down there. But anyway, now something different. I generalized this fundamental notion of Poissonian pair correlation to higher orders. Now I'm going to generalize this in another manner, in a different way. And I'm going to generalize it by changing the scale. So here's the scaling, what was the definition? Anyway, we have an S over N. If you take some parameter 0, beta between 0 and 1, you can consider a different correlation constant function. Let's call it R2 beta S and N. And now this counts how many distinct pairs M and N we have. Oops. And now that we change this scale here, you have 2s over n to the beta. You have n square many points, and you need to normalize by a different factor. You need to normalize by n to the 2 minus beta. And we say that the sequence Xn has beta PPC, beta Poissonian pair correlations, or Poissonian pair correlations with parameter beta. If this counting function converges to 2s for all scales as. Now, what happens when you examine these variants? When you change this scale there, you let, okay, of course, for beta equals 1, we get in the previous setup, right? What happens if we get, if we take smaller values of beta there? First of all, for the case beta equals 0, I will write it as a result. Apparently it must have been known, but we couldn't find it anywhere. So we present it as a new result. And this says, basically, can I correct something here? I will write it in green message. This happens for beta greater than 0, strictly greater than 0. But when beta equals 0, for beta equals 0, you need this limit here to be equal to 2s for all s of most half. Because when beta equals 0 here, this is constant, so this cannot get bigger than a half. It can go to at most a half. So if you raise the values of s, if you take s greater than a half, you cannot find, you cannot expect this to be great, to converge to s. It's just a technical detail. And we show that the sequence Xn has 0 PPC, even only if it is UD mod 1. So 0 PPC turn out to be equivalent to uniform distribution. And now what happens for the other choices of the scale beta? What happens when you let the beta go between 0 and 1? What happens when you examine what is between uniform distribution and PPC, the classical PPC?
The bigger beta, the stronger the statement.
Yeah.
So beta equals 1,
Right.
cover the.
Right. So this is what we showed. So when you increase the beta, you move to a notion which is actually strictly stronger. But it wasn't that trivial in the beginning, because we were thinking maybe for beta less than 1, they are all equivalent to uniform distribution. But it's not.
It's like an effective state. You have a neighborhood of the diagonal which shrinks with n.
Right.
And when beta is 0, the neighborhood of the diagonal is static. It's just
Right.
S thickening of the diagonal. And so it's just you're looking at the square, and you have this random collection of pairs, points x little n, x little m, and they are equidistributed. You think they might, or they're supposed to equidistribute them. Your zero theorem tells me that your beta equals 0 tells me that knowing that that like small neighborhoods of the diagonal are obtaining the expected weight is the same as the original sequence being equidistributed in the unit interval. Now, if you take beta bigger than 0, then suddenly the neighborhood of the diagonal shrinks with the rate. And the statement of being R2 beta Sn equals 2s as n goes to infinity is an effective statement regarding how many pairs are falling in this shrinking neighborhood of the diagonal.
Right,
So
right.
it seems to be like as beta grows, it's a stronger and stronger statement. So you are extracting more and more information out of it.
So indeed, I haven't imagined. Okay, I visualize these motions so that what is the fair share of every point gets around it, but I haven't thought of the image with the diagonal.
Maybe we can speak about it.
Yeah. Right. So if you take, first of all, if you take alpha less than beta, then if xn has beta BTC, then it also has alpha BTC. And number 2, for any choice of the scale beta, we can find the sequence yn that has alpha BTC for all alpha less than beta, but does not have alpha BTC for any alpha greater than beta. So when you move from 0 to 1 towards 1, you get a spectrum of motions that are like genuinely stronger. And now, what is like the most impressive thing in my opinion?
And these examples are physical constructions.
Yeah. In the second point, you mean? Right. Even though you moving from 0 to 1, you get notions which are stronger and stronger, and they go towards the classical notion of PPC. From some point of view, when beta is less than 1, you can group the beta PPC into one bunch of notions, into one like weaker correlations. They have a different nature from some point of view, which I'm going to explain now. So first of all, take some beta strictly less than 1, and suppose there exists some scale S not greater than 0. Such that the theta counting function, the beta correlation counting function converges to 2S for all small scales under this S naught. Then the sequence has beta PPC. In other words, if this convergence holds, from for all S between 0 and some value S naught, it will hold for all S. It was very surprising. And also,
That's not true for a beta equals 1.
right. So this is why I said that these notions differ by nature from the classical notions of PPC, because if you take some capital S greater than 0, and you try to see if this happens in the classical PPC, it will fail. Then you can construct a sequence Xn with a correlation counting function converging to 2S for all S smaller than this bound, this value. And the sequence cannot just fail to have PPC. You can also choose it to fail to have uniform distribution. Do I have time left?
And say 20 more minutes, even more, I think.
Okay. Maybe, I don't know. Do you want my favorite open problem on the field, or?
Yeah.
These are correlations on like fixed point sequences. Another, yeah.
Why is this discussion only on the interval, not in some? It makes sense to speak about like a metric space with a nice measure on, similarly to the big measure on the. Is it important to talk about the unit interval?
So what would your definition be in
Uniform distribution of a sequence would be like a counting measure on x1 up to xn, converges mixed out with the measure that you gave.
Right.
And then your pair correlation thing or some would be to look at the x pairs, xi, xj, and ask, do they fall near the diagonal in capital X times capital X, which supports mu times mu, and the delta neighborhood of the diagonal has a weight, or S neighborhood
Right,
of the
this
diagonal,
would
and then you would expect that the S neighborhood of the diagonal would weigh like 1 over n squared times the number of pairs xi, xj, which falls in this S neighborhood of the diagonal, or
right. I think this was the treatment of Markov paper. He did it like in the arbitrary setting on manifolds and with some appropriate
and he
weight.
has like a theory developed.
Basically, he generalized PPC implies UD result in this setup, but I'm not sure about. I think he does not do anything with weak correlations. So one open problem for the end. These are correlations of fixed point sequences. another way to view static correlations is to take some like some subset of the positive integers. And then consider the sequence an times x, where x is in the unit interval. And you study the behavior of this sequence from a metric point of view with respect to x.
Mod one.
Hmm?
Yeah, mod one.
Right. And yeah, everything is mod one. I should write fraction parts here. For example, of course, you suspect that when the integers form a Lacunary sequence, A and X has Poissonian pair correlations almost surely. Not just Poissonian pair correlations, everything when this sequence is Lacunary, everything here behaves like independent random variables, almost surely.
Lacunary means
Master than number two.
master.
An plus 1 over an greater than some k greater than 1. Roll 1 n. So in particular, so the n is a line. What else? Also, the same happens when an is like the powers of some integer, some power of integer. But of course, it has to be at least 2. There is a series of results, first result by Reichleiner and some others, that connect the pair correlations, the Poissonian pair correlations with this sequence with the additive energy of this. On the other hand, if you take an to be the primes, this does not have EPC for almost all x. There are many other cases that we consider, many other choices. And the point is, for any such subsequent integers, take a set, I will call it PA, which is the set of x here, such that A and x has Poissonian pair correlations. Is the Lebesgue measure of this set always 0 or 1? So does there is there a 0-1 law here? This is a nice one for the students and for the older students. Okay. Let's okay. Why do we expect that there will be a 0-1? Because we have not found anything that disproves it. No, because there are so many examples. This with explicit choices of weightages, when the sequence has Poissonian pair correlations for almost all x, or when there are like examples of sequences which fail to have Poissonian pair correlations. These examples also fail to have for almost all x. For example, if this set here has big additive energy, has additive energy at the maximum possible order of magnitude, then it looks like a geometric progression, an arithmetic progression, sorry. So this sequence again fails to have Poissonian pair correlations for almost all x. Here is the crazy. Like I try to see what happens if you multiply this by 2. I try to examine if this is 2 invariant set. And then it brings you to another notion of pair correlation, which are homogeneous pair correlations. And I don't know.
This would be interesting even if you assume some structure in A.
When you assume some structure in A, it depends on what you mean structure. Like
You just mentioned the invariants and other kinds.
no, trying to answer this. If you try to answer this, it's natural to consider this set is to invariant.
Natural to consider.
Like natural to examine if this set is to invariant. Yeah, the question I ask myself is this set to invariant, but this doesn't go anywhere.
Right. And somehow it needs to. Two and your sequence needs to talk to each other in order for it to be able to see.
Yeah. More questions? No?
Yeah.